Tonight, we're going to travel farther than most people ever let themselves imagine. Not just to the moon, not just to Mars, but past the planets, past the edge of the solar system, into the black gulf between stars, and beyond that, into the space between galaxies themselves. You've probably heard that space is dangerous, a place with no air to breathe and no warmth to hold on to. But here's what almost nobody tells you. The danger doesn't stay the same the farther you go. It gets worse. Much worse. Each step outward strips away another layer of protection, another assumption you didn't even know you were making, until you're left in an environment so hostile, so absolute in its indifference, that even the toughest materials we've ever built start to fail. By the end of tonight, you're going to understand exactly why the deeper you travel into space, the more space itself seems to turn against you. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start close to home. Right now, you are standing on the surface of a planet that is doing an enormous amount of invisible work to keep you alive. An atmosphere presses down around you, shielding you from radiation and burning up debris before it reaches the ground. A magnetic field, generated deep within the molten iron core, wraps around the entire planet and deflects charged particles streaming from the sun. You can actually see this protection at work in the aurora. Think of the magnetic field like a funnel. It can't stop the solar wind completely, so instead, it grabs those particles and channels them down toward the poles, away from everywhere else. That's why the aurora only shows up near the top and bottom of the planet, never in the middle. The particles are getting swept there on purpose by the shape of the field itself. Once they arrive, they crash into the upper atmosphere, and that collision is what makes the sky glow. Most people just see something beautiful. What they're actually watching is radiation being steered away from the rest of the planet and burned off in one small, contained area, instead of reaching the ground where you're standing. Gravity holds you to the surface with a steady, reliable pull. Temperatures stay within a narrow band that allows liquid water to exist almost everywhere you look. None of this feels remarkable because it's constant. You've never experienced anything else, so it doesn't register as protection. But it is protection. Layered, overlapping, redundant protection, built up over billions of years, and every single layer of it disappears the moment you leave. Not gradually, all at once. And what replaces it is not neutral emptiness. It's an environment that becomes more dangerous. In more ways, the farther from Earth you travel. Let's start with the boundary you cross first. Low orbit. This is where the International Space Station flies, a few hundred miles above the surface. It sounds close, and in cosmic terms, it is close, but it's already a completely different world. At this altitude, you are technically still within Earth's magnetic field, which offers some protection from the worst of the sun's radiation. But you are also moving through a region littered with debris. Old rocket stages, dead satellites, flecks of paint, bolts, fragments from past collisions. All of it traveling at speeds around 17,000 miles per hour. At that velocity, even a paint fleck carries the destructive force of a small bullet. A fragment the size of a marble can punch through a spacecraft's hull. There are tens of thousands of tracked objects in orbit around Earth, and millions more too small to track at all. The scale of this problem has grown substantially in recent years. With the rise of large satellite constellations, groups of thousands of small satellites launched together to provide services like global internet coverage. These have added tens of thousands of new active objects to low orbit within just the past few years alone. Each one requires its own collision avoidance planning, and each one adds, however slightly, to the long-term congestion of the orbital environment closest to home. Astronauts on the space station have had to shelter in escape capsules because debris was projected to pass uncomfortably close. Mission controllers on the ground spend a portion of every single day simply watching the sky above the station. They're calculating whether anything is on a path that might intersect with it and adjusting the station's orbit slightly when the odds of a close pass rise too high. This process is known as a conjunction assessment. It involves comparing the tracked orbital paths of tens of thousands of objects against the station's own path and flagging any pair whose predicted distance falls below a safety threshold. In cases where the risk crosses a certain probability, it means commanding a small engine burn to nudge the station's orbit just enough to widen the gap. This happens routinely, several times a year, sometimes with only hours of warning. There's a term for the worst-case version of this problem, something called Kessler syndrome, named after the scientist who first described it in the 1970s. The idea is unsettling once you understand it. If enough objects collide in orbit, each collision creates more debris. That debris goes on to cause more collisions, in a runaway cascade that could eventually turn certain orbital regions into fields too dangerous for any spacecraft to safely pass through. We are not there yet. But the amount of debris in orbit has been steadily increasing for decades. Every rocket launch, every discarded stage, every defunct satellite adds slightly to the problem. This isn't purely theoretical. In 2009, an active communications satellite and a defunct Russian satellite collided directly over Siberia, both traveling at orbital speeds. The impact instantly created well over 2,000 pieces of trackable debris, along with countless smaller fragments, too small to catalogue. It scattered wreckage across a wide range of orbital altitudes that operators still have to account for today, more than a decade later. A single collision, in a matter of seconds, added a measurable, lasting increase to the total debris hazard. Every other spacecraft sharing that region of orbit now faces it. This is the safest region of space humans regularly occupy, and it already requires constant vigilance, tracking systems, and the willingness to move an entire space station out of the way of a piece of metal smaller than a coin. Even objects too small to track present a genuine hazard in this region. Micrometeoroids, tiny natural particles left over from comets and asteroids, strike spacecraft constantly. Most are smaller than a grain of sand, but they travel so fast, sometimes tens of thousands of miles per hour relative to the spacecraft they encounter, that even a particle that size can chip protective glass or pit an exposed surface. Windows on past missions have shown small circular pits from these impacts, evidence collected and studied after the spacecraft returned to Earth. On one occasion, a tiny piece of debris, likely a paint fleck or a small metal fragment, struck a window on the space station with enough force to leave a noticeable chip. It's a reminder that even the smallest object becomes dangerous once you add enough velocity. Layer onto this a second, quieter hazard that has nothing to do with impacts at all. Thermal cycling. A spacecraft in low orbit passes in and out of Earth's shadow roughly every 90 minutes. It moves from direct, unfiltered sunlight into complete darkness and back again, over and over, multiple times a day. In sunlight, exposed surfaces can heat to well over 200 degrees Fahrenheit, or about 93 degrees Celsius. In shadow, those same surfaces can plunge to roughly negative 250 degrees Fahrenheit, or about negative 157 degrees Celsius. That happens within a matter of minutes. That swing, from scorching heat to bitter cold and back again, happens on a loop for as long as the spacecraft remains in orbit, and materials expand and contract every single time. Over months and years, this repeated stress fatigues metal, degrades seals, and weakens joints in ways that a single dramatic failure never would. It's a slow accumulation of tiny fractures that eventually add up to something serious. That's the baseline. And it only gets more demanding from here. Move outward, beyond low orbit, and you enter the region where Earth's magnetic field starts doing something unexpected. Instead of simply deflecting radiation away, it captures some of it. These are the Van Allen belts, two donut-shaped regions of trapped, high-energy particles that circle the planet. The inner belt sits roughly 1,000 to 8,000 miles above the surface. The outer belt extends from around 12,000 to 25,000 miles out. Inside these belts, protons and electrons move at nearly the speed of light, trapped by the magnetic field like water swirling in a whirlpool. Except this whirlpool is made of radiation intense enough to damage electronics and pose a serious threat to unshielded human tissue. The inner belt is dominated mostly by high-energy protons, remnants of cosmic rays that struck the upper atmosphere and knocked particles loose. Those particles then became trapped by the magnetic field. The outer belt is made mostly of electrons, and it's far more variable. It swells and shrinks in response to solar activity, sometimes by a factor of 100 within a single day. Spacecraft electronics passing through these belts have to be hardened against the radiation. And even then, satellites operating in or near the belts experience a shorter operational lifespan because of the constant particle bombardment degrading their components over time. These belts were discovered almost by accident, detected by instruments aboard Explorer 1, the first satellite launched by the United States, in 1958. Physicist James Van Allen noticed the radiation readings behaved strangely as the satellite passed through certain altitudes. At times, the readings spiked so high that the instrument appeared to stop working entirely, when in reality, it had simply been overwhelmed by far more radiation than anyone had anticipated finding in orbit. It was a genuine surprise at the time. It was one of the first indications that near-Earth space was a far more energetic and complicated environment than scientists had assumed before actually sending instruments up to measure it directly. The Apollo astronauts had to pass through these belts on their way to the moon. Mission planners chose trajectories and timing specifically to minimize the exposure, moving through the most intense regions quickly rather than lingering. They threaded a narrow corridor through the belts, where the radiation intensity was comparatively lower. Even with that care, astronauts absorbed measurable doses of radiation during the crossing. Those doses were carefully tracked and remain part of the historical record of human spaceflight. This is still relatively close to home, closer to Earth than the Moon. And already, the environment contains invisible bands of trapped radiation intense enough to require careful planning just to survive passing through them. Keep going. And the Moon itself waits about 238,000 miles from Earth on average. Once you're out past the belts, you're mostly clear of trapped radiation, but now you're exposed to something else entirely. Direct, unfiltered space weather. The sun is not a calm, steady light bulb sitting quietly in the sky. It is a churning ball of plasma, constantly throwing material outward in every direction. The solar wind is a continuous stream of charged particles flowing from the sun's outer atmosphere at speeds often exceeding 1 million miles per hour. On top of this steady wind, the sun periodically erupts. Solar flares release bursts of radiation across the electromagnetic spectrum, arriving at the speed of light itself. That means there is essentially no warning before the radiation reaches a spacecraft or an astronaut on the lunar surface. Coronal mass ejections are even more dramatic. They hurl billions of tons of magnetized plasma into space in a single event. That plasma travels slower than the initial flash of radiation, but still arrives within hours, carrying a secondary wave of high-energy particles behind it. When a large coronal mass ejection reaches Earth, it can trigger geomagnetic storms strong enough to disrupt power grids and damage satellites. It can also endanger astronauts caught outside the protection of Earth's magnetic field. The most powerful documented solar storm in recorded history struck Earth in 1859, an event now known as the Carrington event. It was so intense that telegraph systems around the world sparked and failed, and auroras were visible far outside their normal range, reportedly bright enough to read by at night in places that never see them. If an event of that scale occurred today, the damage to modern satellite systems and power infrastructure would be immense. Some estimates suggest the economic cost of a comparable storm striking a modern, electricity-dependent society could run into the hundreds of billions of dollars. From damaged transformers and satellites to weeks or months of disrupted power in affected regions. A smaller but still significant storm in 1989 knocked out the entire power grid across the Canadian province of Quebec within seconds. It left millions without electricity for hours during the cold of a March night. It was a comparatively modest event by Carrington standards, yet still large enough to disable critical infrastructure almost instantly. If an event of that scale occurred during a crewed mission beyond Earth's magnetic field, the radiation dose delivered to an unprotected astronaut could be fatal within hours or days. That depends on the intensity and how much shielding was available. On the lunar surface, or in transit to the Moon, there is no thick atmosphere and no strong planetary magnetic field standing between you and this radiation. A large solar particle event during a moon mission could deliver a radiation dose in a matter of hours that would otherwise take years to accumulate. Apollo astronauts were lucky. No major solar storm occurred during any of the crewed lunar missions. Though one significant event happened in the gap between two of them, in August of 1972, between Apollo 16 and Apollo 17. Had the timing overlapped with a crew on the lunar surface or in transit, the radiation exposure could have been severe enough to cause acute radiation sickness. In a worst-case scenario, it could have been lethal. Modern forecasting has improved considerably since the Apollo era, with satellites now stationed specifically to watch the sun and give warning of an approaching storm. But even the best current forecasting can typically only provide a warning window of somewhere between 15 minutes and roughly a day, depending on the type of event. That's barely enough time to seek shelter on the lunar surface, and nowhere near enough time to abandon a mission already committed to a distant trajectory. This is the Moon, our closest neighbor, barely 250,000 miles away, and it already sits exposed to a hazard capable of delivering a lethal radiation dose with little warning. The farther you go, the longer you're exposed, and the fewer places there are to hide. There's also the problem of lunar dust. It sounds minor compared to radiation, but it turned out to be a serious operational hazard during the Apollo missions. The Moon has no atmosphere and no weather to smooth down its surface material. So lunar dust particles remain jagged and sharp at a microscopic level, almost like tiny shards of glass, rather than being worn round the way dust and sand are on Earth. This dust clung to spacesuits, damaged seals, and ground away at mechanical joints. It irritated astronauts' eyes and lungs when it made its way into the lunar module. It's a small detail in the larger picture, but it illustrates something important. Every new environment brings hazards that are unique to it. Hazards nobody would think to prepare for until they actually got there and encountered them firsthand. The Moon adds one more challenge that has nothing to do with radiation or dust at all. An extreme swing in temperature, driven simply by the absence of any atmosphere to moderate it. A single lunar day, from sunrise to sunrise, lasts about 29.5 Earth days. That means any single location on the surface experiences roughly 2 weeks of continuous sunlight, followed by roughly 2 weeks of continuous darkness. During the lunar day, surface temperatures in direct sunlight can climb to around 250 degrees Fahrenheit, or about 121 degrees Celsius. During the 2-week lunar night, with no atmosphere to retain any warmth at all, temperatures can plunge down to around -208 degrees Fahrenheit, or about -133 degrees Celsius. That's a swing of over 450 degrees between one lunar day and the next lunar night, at the same physical location. Any equipment or habitat left on the surface has to be engineered to survive both extremes reliably, again and again, for as long as the mission requires. Push outward past the Moon into what's called cislunar space, and then beyond, toward Mars. At its closest, Mars is about 34 million miles from Earth. At its farthest, when the two planets are on opposite sides of the Sun, that distance stretches past 250 million miles. A crewed mission would likely take somewhere between 6 and 9 months just to get there, one way, using current propulsion technology. The exact duration depends heavily on the alignment of the two planets' orbits at the time of departure. During that entire transit, there is no planetary magnetic field protecting the spacecraft. There is no thick atmosphere overhead. There is only the metal hull of the ship and whatever shielding the crew can carry with them. For 6 to 9 months, every person on board is bathed continuously in galactic cosmic radiation. It's a steady rain of high-energy particles originating from outside the solar system entirely, likely accelerated by the shock waves of ancient star explosions. These are particles that have been traveling through the galaxy for millions of years before finally intersecting with a spacecraft's path. Unlike solar radiation, galactic cosmic rays are extremely difficult to shield against. Many of these particles carry so much energy that when they strike a spacecraft's hull, they don't just get absorbed. They shatter atoms in the material itself, producing a spray of secondary particles that can be almost as damaging as the original cosmic ray. Engineers call this phenomenon secondary radiation. Thicker shielding doesn't always help. Past a certain point, adding more material actually increases the secondary particle shower rather than blocking it. That means simply piling on more mass. The traditional solution to almost every other spacecraft problem actually works against you here. This creates a genuinely counterintuitive engineering puzzle, since intuition suggests that more shielding should always mean more protection. In reality, mission designers have to calculate an optimal thickness for every material used. Thin enough to avoid triggering excessive secondary radiation, but thick enough to meaningfully slow the primary particles arriving from outside. a balance that shifts depending on the exact composition of the shielding material chosen. Water, ironically, turns out to be one of the more effective shielding materials available, both because of its hydrogen content and because it's already something a crew has to carry in large quantities anyway. That's led some mission designs to propose lining crew quarters with water tanks, doing double duty as both a life support resource and a radiation barrier at the same time. Studies of the radiation exposure a Mars crew would receive suggest it could approach or exceed career radiation limits for astronauts, all from a single round trip. Those limits were established specifically to keep lifetime cancer risk within an acceptable range. To put this in terms researchers actually use, radiation exposure is measured in units called millisieverts, a measurement of the biological effect radiation has on tissue. A single chest X-ray on Earth delivers roughly 1/10 of 1 millisievert. An average person living on Earth's surface absorbs somewhere around 3 millisieverts per year from natural background sources combined. Astronauts aboard the space station, still partially protected by Earth's magnetic field, absorb roughly 80 to 160 millisieverts over a 6-month stay. That's already dozens of times higher than the natural rate on the ground. A round trip to Mars, with no planetary magnetic field to help for most of the journey, has been estimated in various studies to deliver somewhere in the range of 600 to 1,000 millisieverts total. That depends on solar activity, mission duration, and shielding. That's a dose that meaningfully raises lifetime cancer risk. In a bad-case scenario involving an unshielded solar storm during transit, it could climb high enough to cause acute radiation sickness on its own. Cancer risk increases. Cognitive effects from radiation exposure are still being studied. Some research on laboratory animals suggests that high-energy particle radiation may affect memory and decision-making in ways that ordinary radiation exposure on Earth does not fully replicate. Once you factor in a solar storm occurring during transit, with no fast way to get home, the mission becomes a genuine gamble against the physics of an unshielded universe. Beyond radiation, there's the physical toll of extended weightlessness. Without gravity's constant pull, bones lose density at a rate of roughly 1 to 1.5% per month in certain regions of the skeleton. That's a rate far faster than age-related bone loss on Earth. Muscles atrophy without the resistance of normal movement. That requires astronauts to exercise for roughly 2 hours every single day just to slow the decline. Fluid shifts toward the upper body in microgravity. That's been linked to changes in eye shape and vision problems that, in some astronauts, have not fully reversed even after returning to Earth. Researchers now refer to this as spaceflight associated neuro-ocular syndrome, involving swelling around the optic nerve and a flattening of the eyeball itself. These are changes that have been documented through imaging on astronauts returning from missions of 6 months or longer. The exact cause is still being researched, but the leading theory involves fluid that would normally be pulled toward the legs by gravity, instead settling around the head and eyes for the full duration of the mission. It's a slow, cumulative pressure with effects that, on a mission to Mars lasting far longer than a typical space station rotation, could potentially be more pronounced. The immune system behaves differently in space as well. Some studies show changes in how certain immune cells function during long-duration missions, though the full implications are still being studied. None of this is fatal on its own, but stack it together over a 9-month transit to Mars, then months on the surface, then another 9-month transit home. It represents a cumulative physical toll that current medicine only partially understands and cannot fully counteract. 6 to 9 months to reach Mars. A crew of 4, undertaking a mission of this length, would require an enormous quantity of consumables, even with efficient recycling in place. Food alone is typically estimated at somewhere around 1.5 to 2 pounds per person per day of packaged mass. That adds up to several tons of food across a mission spanning more than 2 years when the surface stay and return trip are included. Every extra pound of food, water, spare parts, and equipment has to be launched from Earth's surface at enormous cost and carried the entire distance. That's part of why closed-loop recycling of air and water matters so much. It's simply not feasible to carry enough consumable water for years without recovering and reusing the vast majority of it along the way. Then, the surface itself, where the atmosphere is too thin to block meaningful radiation at less than 1% of Earth's atmospheric pressure. And there's no global magnetic field at all, because Mars lost its dynamo billions of years ago when its core cooled enough to stop generating one. The Martian surface brings its own additional hazard, one that has nothing to do with radiation at all. Dust storms on Mars can grow large enough to envelop the entire planet, lasting for weeks at a time. One such global storm in 2018 was thick enough to block sunlight so completely that a solar-powered rover operating on the surface lost contact with Earth entirely. Its batteries drained in the darkness, and it never woke up again. For a future crewed mission relying on solar power to generate electricity and run life support, a storm of that scale, arriving at the wrong time, could turn a survivable mission into a genuine emergency, cutting off power exactly when it's needed most, with no possibility of a quick resupply from Earth to make up the difference. Then, 6 to 9 months back. The farther out you go, the longer the exposure window stays open, and there's no way to shorten it without fundamentally new propulsion technology that doesn't yet exist. Beyond Mars, the asteroid belt spreads out in a wide ring, filled with countless rocky bodies, ranging from dust grains to objects hundreds of miles across. Contrary to how movies portray it, the asteroid belt is not a dense, chaotic field where ships have to dodge rocks every few seconds. The average distance between objects is vast, often millions of miles, and several spacecraft have passed through it without any special maneuvering at all. But that doesn't mean it's harmless. It means the danger there isn't from density. It's from the sheer number of objects whose orbits are not fully mapped. Their paths can shift slightly over time due to gravitational nudges from nearby planets and from each other. And their collisions with one another occasionally send fragments onto trajectories that eventually cross paths with Earth. There are more than 1 million known asteroids larger than roughly 0.6 of a mile across within the belt, and countless smaller fragments that have never been catalogued at all. For a spacecraft passing through, the real risk isn't a dramatic collision course with a visible asteroid. It's the small, untracked debris, fragments a few inches across, moving at speeds that would make even a minor impact catastrophic for an unshielded hull. The scale of energy even a modest-sized object carries was demonstrated dramatically in 2013. A rocky object, roughly 60 feet across, far smaller than anything in the main asteroid belt would need to be to cause real damage, entered the atmosphere above Chelyabinsk, Russia, completely undetected in advance. It exploded in the atmosphere with a force estimated at nearly 30 times the energy released by the atomic bomb dropped on Hiroshima. It shattered windows across a wide area and injured over 1,000 people from flying glass, without ever directly striking the ground in one solid piece at all. That object came from within our own solar system, on an orbit nobody had tracked. It illustrates just how much remains uncatalogued, even close to home, let alone within the vastly larger and more distant asteroid belt itself. In response to exactly this kind of blind spot, space agencies have begun developing what's now called planetary defense. Dedicated efforts to catalog near-Earth objects and to test methods for actually deflecting one if it were ever found on a collision course. In 2022, a spacecraft was deliberately crashed into a small asteroid moonlet as a test of this idea. It successfully changed the moonlet's orbital period by a measurable amount, proof that a kinetic impact could, in principle, nudge a hazardous object off a collision course if it were detected early enough. Early enough remains the key phrase. Objects the size of the one that exploded over Chelyabinsk remain extremely difficult to detect until they are already very close. And the vastly larger population of small, dim objects scattered throughout the asteroid belt and beyond means new discoveries continue to be made even now. The largest object in the asteroid belt, a dwarf planet named Ceres, was studied up close by the Dawn spacecraft. It found evidence of ice and even possible remnants of a subsurface ocean. A reminder that even in this rubble-strewn region, there are worlds complex enough to be worth genuine scientific curiosity, alongside all the hazards. Beyond the belt, the outer solar system opens up, and distances start to become almost impossible to hold in your head. Jupiter sits about 484 million miles from the Sun, on average. Its moon, Europa, is one of the most compelling targets in the search for life beyond Earth, because of the liquid ocean believed to exist beneath its icy shell. But it orbits within one of the most intense radiation environments in the entire solar system. Jupiter's own magnetic field is enormously powerful, roughly 20,000 times stronger than Earth's. It traps charged particles into radiation belts so severe that spacecraft visiting the Jovian system have to be specifically hardened against the exposure, or they simply won't survive long enough to complete their mission. The Galileo spacecraft orbited Jupiter for 8 years. Its electronics were shielded specifically to endure this environment. And even so, the radiation gradually degraded its instruments over the course of the mission. A human standing, unprotected, on Europa's surface would receive a lethal radiation dose in a matter of hours, not from the Sun, but from Jupiter itself. A dedicated spacecraft, launched specifically to study Europa's ice shell and the ocean believed to lie beneath it, was designed with this exact hazard in mind. It was built with thick radiation shielding around its most sensitive electronics, and a flight plan involving repeated close flybys rather than a full extended orbit. That's specifically to limit the cumulative radiation dose the spacecraft itself would otherwise absorb over the course of its mission. At Jupiter's distance, the Sun is so faint it provides barely more light than a bright full moon gives Earth, and yet the local environment is more radioactive than almost anywhere else humans might consider visiting. Distance from the Sun doesn't mean safety. Sometimes it means trading one danger for a different, worse, one generated by something else entirely. Jupiter's innermost large moon, Io, adds another layer to this hostile picture. It is the most volcanically active body known anywhere in the solar system. It constantly resurfaces itself, with eruptions driven by the intense gravitational stresses Jupiter exerts on it. Material ejected from Io's volcanoes actually helps feed Jupiter's radiation belts. It becomes ionized and trapped by the magnetic field, adding to the very radiation hazard that already makes the region so dangerous. It's a system where geology and radiation are directly connected, each one making the other worse. Saturn's moons present a gentler radiation environment. Saturn's magnetic field, while still significant, is nowhere near as ferocious as Jupiter's. But they bring their own extreme conditions. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane and ethane on its surface. Its temperature sits at roughly -290 degrees Fahrenheit, or about -179 degrees Celsius. Cold enough that water ice behaves like bedrock, and any liquid on the surface has to be something other than water entirely. Enceladus, a much smaller moon, ejects plumes of water vapor and ice particles from its south pole. That's evidence of a liquid ocean beneath its icy shell, a genuinely exciting target in the search for life. But it's also a world locked in permanent, bitter cold, with an average surface temperature of about -330 degrees Fahrenheit, or about -201 degrees Celsius. Both worlds were studied closely by the Cassini spacecraft, which orbited Saturn for 13 years, and by the Huygens probe, which Cassini released to descend through Titan's thick atmosphere and land on its surface in 2005. Huygens transmitted images back during its brief descent, before its batteries eventually ran out in the deep cold. It became a permanent, silent piece of hardware resting on an alien shoreline of liquid methane, thousands of times farther from any possibility of repair or retrieval than anything stranded on Earth could ever be. Continue outward, past Saturn, past Uranus, past Neptune, and the character of the danger shifts again. Saturn sits nearly 900 million miles from the Sun. It brings its own version of Jupiter's problem, a strong magnetic field and its own radiation belts, though generally less intense. Saturn's rings are spectacular, but they're also made up of countless particles of ice and rock, ranging from dust to house-sized chunks, all orbiting at high velocity. That adds yet another debris hazard for any spacecraft that gets too close. Some of the larger ring particles move fast enough that a collision would be just as destructive as any encounter with debris closer to Earth. Only here it's naturally occurring, rather than left behind by human activity. Out here, sunlight is so weak it barely qualifies as daylight. At Neptune's distance, roughly 2.8 billion miles from the Sun, sunlight is about 900 times fainter than it is on Earth. Standing on Neptune's largest moon, Triton, the Sun would appear as barely more than an intensely bright star, offering almost no perceptible warmth at all. Temperatures drop to around -350 degrees Fahrenheit, or about -212 degrees Celsius. This far out, solar radiation stops being the dominant hazard, because there's so little solar energy left to be hazardous. Instead, the danger becomes the environment itself, extreme cold that would freeze any unprotected human tissue solid within moments. Cold so severe that many common materials become brittle and prone to fracturing, complicating the engineering of any spacecraft or habitat meant to function reliably out there. Near total darkness that makes navigation and operations extraordinarily difficult. That requires spacecraft to rely far more heavily on artificial lighting, radar, and pre-programmed navigation than anything used closer to the Sun, and a growing dependence on galactic cosmic radiation as the primary hazard. You're now far enough from the Sun that its magnetic field, the heliosphere, offers less and less protection from radiation arriving from interstellar space. Voyager 1 and Voyager 2, launched in the late 1970s, are the only human-made objects to have traveled this far and kept transmitting data back. It took them decades to reach the edge of the solar system. Voyager 1 crossed into interstellar space in 2012, roughly 35 years after launch. Voyager 2 followed in 2018. Neither carries any human passengers, for good reason. No life support system yet devised could keep a person alive for the decades required to travel that far. And even if it could, the radiation exposure accumulated over such a long journey would almost certainly be lethal well before arrival. Both Voyager probes are powered by radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium into electricity. At that distance from the Sun, solar panels would be almost entirely useless. Even these generators are slowly losing power output over time. Mission engineers have had to shut down instrument after instrument over the decades, simply to conserve the dwindling electricity that remains. A slow, managed decline toward the eventual day when the spacecraft will finally go silent. Each Voyager probe also carries a golden record, a phonograph disc containing sounds and images meant to represent Earth, along with instructions for playing it. It's included in case either spacecraft is ever encountered by someone or something else out there. It's a small, hopeful gesture attached to a mission that otherwise exists mostly as a demonstration of just how far current technology can reach, and just how little of the true distance to another star that reach actually covers. Even after traveling for decades and covering billions of miles, both Voyager probes remain, in cosmic terms, only barely beyond our own solar system's front doorstep. This is the edge of what we can call our solar system's neighborhood. And it took the fastest, most sophisticated spacecraft humanity has ever built the better part of 4 decades just to reach it. The boundary itself is not a sharp line, but a layered structure. It's built up by the collision between the Sun's outward-flowing wind and the thin gas that fills interstellar space. First comes the termination shock, the point where the solar wind abruptly slows as it begins to push against the surrounding interstellar material. That solar wind has been traveling outward at over 1 million miles per hour. Beyond that lies the heliosheath, a turbulent, compressed region where solar wind particles pile up and swirl before finally losing momentum entirely. And beyond that, at the very edge, sits the heliopause, the true boundary where the Sun's influence effectively ends, where the pressure of the wider galaxy takes over. When Voyager 1 crossed this boundary in 2012, scientists confirmed it, not by any dramatic visual change, since there was nothing to see. They confirmed it through a sudden and sustained shift in the type of charged particles the spacecraft's instruments were detecting. Solar particles dropped away almost entirely, replaced by the steady hum of galactic cosmic rays arriving from far beyond the solar system. It was, in a very real sense, the moment our Sun's protection ran out completely for that spacecraft. A boundary crossing with no fanfare, no light show, just a quiet change in the data streaming back across billions of miles. Instruments aboard Voyager also detected something unexpected just beyond the boundary. Evidence that the Sun's own magnetic field doesn't simply end abruptly, but drapes and folds against the surrounding interstellar magnetic field. The two fields press against each other in a turbulent boundary layer, rather than meeting in a clean, simple line. It was a small but telling reminder that even our understanding of where the solar system truly ends remains built on data from a single pair of spacecraft, gathered one narrow path through an otherwise unmapped boundary at a time. Now, step outside the heliosphere entirely, into true interstellar space. This is the region between star systems, and here, the danger changes in kind, not just in degree. Inside the solar system, no matter how far out you travel, you're still within reach of the sun's magnetic bubble, however weak it becomes at the edges. That bubble, the heliosphere, deflects a portion of the galactic cosmic radiation that would otherwise reach you directly. Step outside it, and that partial shield disappears. You are now fully exposed to the unfiltered radiation of the galaxy. A constant bombardment of high-energy particles from exploded stars scattered across thousands of light-years, arriving from every direction. Essentially, nothing stands between you and them, except whatever shielding your spacecraft physically carries. At the same time, temperatures out here settle at just a few degrees above absolute zero. That's dictated by the faint afterglow of the universe's own formation, the cosmic microwave background. It's a uniform whisper of radiation left over from a much earlier era of the universe, filling every direction of space almost perfectly evenly. There is no starlight bright enough to warm anything. Interstellar space is not, however, a perfect vacuum in the strictest sense. It contains an extremely thin scattering of gas and dust, mostly hydrogen and helium atoms left over from the earliest epochs of the universe, along with microscopic dust grains produced by dying stars. The density is almost incomprehensibly low, often just a handful of atoms per cubic inch. But a spacecraft moving fast enough, on the order of tens of thousands of miles per hour or more, would still experience these atoms as a kind of faint, continuous friction. At sufficiently extreme velocities, approaching a meaningful fraction of the speed of light, even individual dust grains could strike a hull with the force of a small explosive, simply because of how much kinetic energy their velocity would carry. This is one of the underappreciated engineering problems of any theoretical high-speed interstellar mission. Interestingly, our own solar system happens to sit inside a relatively low-density region of interstellar gas that astronomers call the local bubble. It's a cavity roughly 1,000 light-years across, likely carved out by the shock waves of ancient supernova explosions that occurred nearby millions of years ago. That's left behind a pocket of unusually thin gas surrounding our Sun and its nearest neighboring stars. It's a small, fortunate detail, one more layer of relative calm surrounding our particular corner of the galaxy. Though it says nothing about the density of gas and dust a spacecraft would eventually encounter, once it traveled far enough to exit this bubble and enter the denser interstellar material beyond it. It's not just about getting the propulsion right. It's about surviving contact with the thin scattering of matter that fills even the emptiest regions of the galaxy. The nearest star system, Alpha Centauri, sits about 4.24 light-years away. In miles, that's roughly 25 trillion miles. Even at the speed of the fastest spacecraft ever built, reaching it would take tens of thousands of years. Voyager 1, moving at around 38,000 miles per hour relative to the Sun, would need roughly 75,000 years just to cover that distance. And it isn't even headed toward Alpha Centauri. Think about what that number actually represents. An unshielded human wouldn't need to worry about starvation or suffocation on such a journey. The accumulated radiation dose alone, sustained over centuries, let alone tens of thousands of years, would cause fatal damage long before any other failure occurred. This is the true void. Not empty in the sense of being calm, empty in the sense of offering nothing at all. No warmth, no shelter, no protection. Only distance stretching outward in every direction, and radiation filling that distance uniformly, indifferently, everywhere at once. there's an additional, less obvious hazard scattered through this emptiness, one that has only become clear to scientists in the last several years: rogue planets and interstellar objects. Not every planet stays bound to a star. Gravitational interactions during the early chaotic formation of a solar system can fling a planet entirely out of orbit. It drifts alone through the galaxy, warmed by nothing, lit by nothing, its only light, the faint glow of distant stars scattered across an otherwise black sky. Estimates suggest there could be billions of these rogue planets wandering the Milky Way, unbound to any star. They're essentially invisible, unless one happens to pass directly in front of a background star and briefly bend its light through gravity. That's the method astronomers actually use to detect them, an effect called gravitational microlensing. It produces only a brief, temporary brightening of the background star, lasting anywhere from hours to weeks, depending on the mass of the invisible object passing in front of it. Some estimates, based on the handful of these lensing events already observed, suggest that rogue planets could actually outnumber the stars that host planetary systems within the galaxy. That means the space between stars may be far less empty of large bodies than the term interstellar space initially suggests. Even though every single one of those wandering worlds remains completely dark and cold, with no star of its own to warm it. Similarly, occasionally an object from another star system altogether passes directly through our own solar system. In 2017, astronomers detected the first confirmed interstellar object ever observed, an elongated body given the name Oumuamua. It moved on a trajectory that made clear it had originated outside our solar system entirely, simply passing through before continuing back out into the galaxy forever. A second interstellar visitor, a comet named Borisov, was detected 2 years later. Neither of these objects posed any danger to Earth. But their discovery confirmed something important: that interstellar space is not simply a static void. It's a place where objects from other star systems occasionally cross paths with our own, unpredictably, on trajectories nobody can forecast far in advance, because nothing was tracking them before they arrived. For any spacecraft attempting a long, slow journey through interstellar space, this adds one more layer of uncertainty to an already uncertain environment. The small but real possibility of encountering something entirely uncatalogued, drifting through the same emptiness, on a path nobody had any way of predicting. Even proposed concepts for faster interstellar travel run directly into this problem. Spacecraft accelerated by powerful ground-based lasers to a meaningful fraction of the speed of light, for instance. The faster you go, the more dangerous even a single dust grain becomes, because kinetic energy increases with the square of velocity. A speck of interstellar dust that would be harmless at conventional spacecraft speeds becomes a serious threat at 20% of the speed of light. It's capable of punching through shielding that would easily stop the same particle moving more slowly. There is, in other words, no version of faster interstellar travel that simply removes the danger. It only changes which danger dominates: radiation and isolation at slow speeds, impact energy and structural stress at extremely high speeds. Underlying every single one of these challenges is a limit that no amount of engineering will ever overcome: the speed of light itself. Nothing with mass can reach or exceed it. Even approaching a meaningful fraction of it requires energy on a scale far beyond anything current propulsion technology can generate. This isn't a temporary technological limitation waiting to be solved by a clever enough engineer. It's a fundamental property of the universe, confirmed repeatedly across more than a century of physics experiments. It means that distance in space isn't just a matter of miles. It's a matter of time that cannot be shortened past a certain point, no matter how much energy or ingenuity is applied to the problem. Every hazard already described, the radiation, the isolation, the impossibility of quick rescue, all of it ultimately traces back to this one unbending limit. Information and matter can only cross the universe so fast. And the universe itself is far larger than that speed can comfortably accommodate. There's a stranger consequence buried in the physics of traveling at a significant fraction of the speed of light, one that has nothing to do with radiation or impacts at all. Time itself would no longer pass at the same rate for the traveler as it does for everyone left behind. This isn't science fiction. It's a well-confirmed consequence of relativity, verified repeatedly through experiments involving fast-moving particles and precise atomic clocks flown on aircraft and satellites. For a crew traveling toward another star at a meaningful fraction of light speed, time aboard the spacecraft would tick forward more slowly relative to Earth. A journey that felt like a handful of years to the crew could correspond to a much longer span of time back home, a gap that would only widen the faster the spacecraft traveled. A crew returning from such a journey, even a successful one, could find that decades or generations had passed on Earth in the time they experienced as only a few years aboard ship. They'd arrive home to a world that had moved on entirely without them, filled with descendants of people they once knew and technology that had continued advancing in their absence. It's a quiet, easily overlooked hazard compared to radiation or structural failure, but it's a real one. A reminder that even a mission that succeeds completely, that avoids every physical danger already described, still carries the traveler permanently out of step with the world they left behind. Among the particles that make up galactic cosmic radiation, one category deserves particular attention. Researchers call them HZE particles, meaning nuclei of high atomic number and high energy, essentially the stripped cores of heavy elements like iron, moving at a significant fraction of the speed of light. These are far less common than lighter particles like protons, but they carry an outsized biological impact. When a single HZE particle passes through living tissue, it can tear a dense, continuous track of damage directly through cells and even directly through strands of DNA. That's a different kind of damage than the more diffuse harm caused by lower energy radiation encountered on Earth. Laboratory studies simulating this kind of exposure in animals have shown effects on the brain and nervous system that researchers are still working to fully understand. Nothing on Earth naturally produces this exact type of radiation in comparable amounts. That means long-duration missions represent a genuinely new kind of biological exposure, one human medicine has limited experience addressing. To study this properly, researchers have built specialized particle accelerator facilities designed to recreate the mix of high-energy particles found in galactic cosmic radiation. That allows controlled experiments on biological tissue that would otherwise be impossible to conduct anywhere outside of actual deep space itself. Even with this dedicated research effort, decades of study have only begun to map out the full range of effects this radiation might have across a mission lasting years. Rather than the weeks or months, such experiments can typically simulate at once. There's already documented evidence of this kind of damage in real astronauts, even from missions far shorter and far better shielded than a journey to another star system would ever be. Studies following astronauts from the Apollo program found a notably higher rate of cataracts later in life. They're the only humans to have traveled beyond Earth's protective magnetic field and into deep space, however briefly. That's compared to astronauts who only flew in low orbit. A pattern consistent with the kind of cumulative lens damage high-energy radiation is known to cause. It's a small, quiet piece of evidence gathered from missions that lasted only days, and it offers a sobering hint at what a mission measured in months, years, or generations might mean for the people undertaking it. There is also a rarer, far more extreme hazard that becomes relevant only across the vast timescales and distances involved in any serious discussion of interstellar travel. The gamma-ray burst. These are the most energetic explosions known to occur anywhere in the universe. They're believed to be produced by the collapse of certain massive dying stars or by the collision of extremely dense stellar remnants such as neutron stars. A gamma-ray burst releases, in a matter of seconds, roughly as much energy as the Sun will produce over its entire multi-billion-year lifetime. That energy is concentrated into narrow, powerful beams of radiation that sweep across the universe like the beam from a lighthouse, visible only to anyone unlucky enough to be standing directly in its path. The initial burst itself typically lasts anywhere from a fraction of a second to several minutes. It's followed by a longer, fading afterglow across other wavelengths that astronomers can study for days or weeks afterward from a safe distance. That lets them piece together the physics of the event, long after the most dangerous, most concentrated radiation has already passed. If a beam like that were to sweep directly across a solar system from a relatively nearby source, the radiation could be intense enough to seriously damage a planet's atmosphere, and any unshielded spacecraft caught in its path. Fortunately, these events are rare, and no known source close enough to pose a serious threat to our solar system is currently positioned to aim one in our direction. But across the almost unimaginable spans of time involved in any long-duration interstellar mission, spans measured in centuries or more, the odds shift. Something this violent, however small the chance, is no longer quite as negligible as it is across an ordinary human lifetime. It's another example of the same underlying pattern. The farther out, and the longer you travel, the more of the universe's rare, violent possibilities you eventually have to reckon with. Simply because more time and more distance means more exposure to events that would otherwise almost never matter at all. This progression isn't random. Near Earth, you're protected by a planetary magnetic field and atmosphere, both generated by processes specific to a rocky world with a molten core. Farther out, within the inner solar system, you still have the Sun's magnetic field and the physical shielding of distance from any single, catastrophic radiation source. Those solar storms remain a serious hazard. Near the giant planets, you trade solar radiation for planetary radiation. Gas giants like Jupiter generate colossal magnetic fields of their own, ones that trap and accelerate particles into belts even more intense than Earth's. At the outer edge of the solar system, both solar and planetary protections fade. Galactic cosmic radiation becomes the dominant threat, arriving steadily from every direction in the sky. And in true interstellar space, that galactic radiation becomes the only environment there is. Unfiltered, constant, combined with cold so extreme, it approaches the theoretical minimum temperature the universe allows. Each region trades one danger for another, or adds a new one on top of what already existed. Nothing gets safer as you go. It only changes shape. There's also the matter of communication, something that doesn't show up in most conversations about the dangers of deep space, but becomes an enormous problem the farther out you travel. Radio signals, even moving at the speed of light, take time to cross distance. From the Moon, a message takes about 1.5 seconds to reach Earth, and another 1.5 seconds for a reply to come back, so roughly 3 seconds round trip. Manageable. From Mars, depending on the planet's positions in their orbits, one-way communication delay ranges from about 3 minutes to over 20 minutes. A simple question and answer exchange could take up to 40 minutes round trip. If something goes wrong on a Mars mission, the crew cannot simply call home and get help in real time. They have to solve the problem themselves. By the time Earth even receives news of the emergency, the situation may have already changed. This is such a significant operational concern that mission planners have already begun training astronauts to make many decisions autonomously, without waiting for approval from mission control. The communication delay makes real-time oversight impossible once a crew is far enough from Earth. From Jupiter, one-way signal delay stretches to around 33 minutes at closest approach and up to about 52 minutes at farthest. From Neptune, it's over 4 hours, one way. A single question, and its answer could take the better part of a working day to complete. And from interstellar space, from a spacecraft approaching another star system, the delay would be measured in years, not minutes or hours. Voyager 1 is now far enough away that a radio signal, traveling at the speed of light, takes over 23 hours to reach it. A single round-trip exchange with the spacecraft, a command sent and a confirmation received, takes roughly 2 full days to complete. And that's with Voyager 1, still only at the outer edge of the solar system's influence. Current plans for renewed lunar exploration have to account for exactly this kind of delay, even at much shorter distances. That includes programs designed to establish a more permanent human presence around and on the Moon. That means building in enough autonomy for crews and habitats to handle routine operations and minor emergencies without waiting on approval from Earth. Every mission beyond low orbit is an exercise in operating independently, rather than one in constant real-time support. At Alpha Centauri's distance, a message sent home would take over 4 years to arrive, and any reply would take another 4 years to come back. A conversation with Earth would unfold across nearly a decade for a single exchange. This means that beyond a certain distance, you are not just physically isolated, you are informationally isolated. Whatever happens to you happens without oversight, without real-time guidance, without the possibility of rescue arriving in any meaningful time frame. Every decision has to be made locally, by whoever is present, using whatever knowledge and equipment they happen to have on hand. The farther you go, the more completely you are cut off from any form of external help. Not because no one cares, simply because light itself isn't fast enough to close the gap in a useful amount of time. Then there's the psychological dimension, which grows heavier the farther from home a person travels, even though it's not a hazard you can measure with a radiation detector. On the space station, astronauts can see Earth out the window. They can watch sunrises and sunsets every 90 minutes as the station circles the planet. Home is visibly, tangibly close. On a mission to Mars, Earth eventually shrinks to a faint blue point of light, indistinguishable from a star, visible only through a telescope aimed in exactly the right direction. Astronauts on such a mission would spend months watching their entire world reduced to a single pixel, and then disappear from naked eye visibility altogether. Psychological studies of long-duration isolation, including research conducted in Antarctic stations and simulated Mars missions, consistently point to real risks. Depression, anxiety, interpersonal conflict, and a phenomenon researchers call the third quarter effect, a dip in morale that tends to occur once a mission passes its psychological midpoint and the ending still feels far away. Crews in these simulated environments have also reported disrupted sleep patterns, irritability, and a gradual narrowing of interests and conversation topics as the mission wears on. A kind of mental fatigue that sets in even when physical health remains stable. One extended simulation, a project called Mars 500, ran in the 2010s. It sealed a crew of volunteers inside a mock spacecraft for 520 days, roughly the length of a real round trip to Mars, without ever actually leaving Earth. Researchers tracked sleep patterns, mood, and group dynamics throughout. Some crew members drifted toward reduced activity and altered sleep cycles as the isolation wore on, becoming less responsive to the outside world, even though nothing about their physical environment had changed. Separately, researchers who study isolated research stations in Antarctica have documented similar patterns across decades of observation. Small teams there spend the dark winter months completely cut off from resupply and often from easy communication. They call it winter over syndrome, involving irritability, difficulty concentrating, and disrupted sleep among people confined together in isolation through the long, sunless winter months. These are the closest real-world analogues available for what extended isolation does to the human mind. And even they fall dramatically short of what a genuine multi-year interstellar journey would involve. Everyone in these Earth-based experiments knew, at some level, that home remained reachable if something truly went wrong. Now, imagine that same isolation stretched not across months, but across years, or decades, or centuries, in a journey toward another star system. There is no version of that mission where crew members can look back and see something familiar. Earth wouldn't just be far away. It would be effectively gone from view, a memory rather than a visible object. Everyone aboard would know that even a message home would take years to arrive, and years more for any reply. Some theoretical proposals for interstellar travel involve so-called generation ships. Spacecraft designed to support not the original crew reaching the destination, but their descendants, generations born, raised, and having lived their entire lives without ever having known Earth directly. The engineering challenge behind a generation ship is staggering, even before accounting for the psychological questions. The vessel would need a fully closed ecological system, recycling air, water, and nutrients indefinitely, growing enough food to sustain a stable population for centuries without any external input at all, essentially replicating, in miniature, the same kind of self-sustaining balance that took Earth's entire biosphere billions of years to develop naturally. Small-scale experiments on Earth have attempted to create sealed, self-sustaining ecosystems. Most notably, a large research facility built in Arizona in the early 1990s, designed to test whether people could live for extended periods inside a fully sealed artificial environment. That experiment revealed just how difficult this balance actually is to maintain. Oxygen levels in that experiment dropped unexpectedly due to unanticipated chemical reactions with the concrete used in construction. Crop yields fluctuated in ways the designers hadn't predicted. Maintaining stable, breathable air proved far more delicate than anyone involved had initially assumed, even with the ability to bring in outside help if something went seriously wrong. A generation ship would have no such safety net. Every one of those same delicate balances would have to hold, uninterrupted, for far longer, with no possibility of outside correction if something began to drift out of equilibrium. Add to that the question of genetic diversity within a small, permanently isolated population. A crew numbering in the hundreds or low thousands would be confined together for generations, with no new genetic input from outside. That would need careful, deliberate management to avoid the health problems that come from a shrinking gene pool. The psychological and social implications of that kind of mission are almost entirely unstudied because nothing like it has ever actually been attempted. Would a society, confined permanently to a single vessel, maintain stable culture and cooperation across dozens of generations? Would the original mission's purpose still hold meaning to people who never chose to undertake it and were simply born into it? What would family and relationships even look like inside a permanently sealed, permanently isolated community? Every person someone might ever meet, argue with, or fall in love with is drawn from the same small, fixed population. For their entire life, generation after generation, with no possibility of new people ever arriving from outside. These aren't questions physics can answer. That kind of isolation is not something human psychology evolved to handle. We are a species shaped by small groups, physical closeness, and constant feedback from our environment and each other. Deep space asks you to give all of that up, indefinitely, with no fallback if it becomes too much to bear. There's another factor that gets worse with distance. It has to do with the reliability of the equipment, keeping everyone alive. Every spacecraft depends on machinery. Life support systems that scrub carbon dioxide from the air, recycle water, regulate temperature, generate power, and maintain pressure. Near Earth, if something breaks, spare parts and even entire crews can be sent up relatively quickly. The space station has been resupplied and repaired continuously for over 2 decades. That's precisely because Earth is close enough to make that possible. On a mission to Mars, resupply becomes essentially impossible during the transit itself. Even after arrival, sending replacement parts would take the better part of a year to arrive, if a launch window even aligns favorably. Earth and Mars only line up for efficient transit roughly once every 26 months. Every component of the spacecraft has to function correctly, or be repairable using only what's already on board, for the full duration of the mission. On a journey to another star system, this problem becomes absolute. There is no possibility of resupply, ever. History already offers a preview of what happens when something goes wrong far from home, even relatively close to Earth by the standards discussed tonight. In 1970, an oxygen tank aboard Apollo 13 ruptured while the spacecraft was on its way to the Moon. It crippled the main service module and forced the crew to abandon their landing entirely. They retreated into the lunar module and used it as a makeshift lifeboat for the journey back. The crew and mission control on the ground worked through a cascading series of improvised fixes, rationing power, water, and breathable air, famously adapting square carbon dioxide filters to fit round receptacles they were never designed for, using nothing more than materials already on board: spare plastic bags, cardboard, and tape. It worked, and the crew returned safely. But the entire episode remains a striking demonstration of how quickly a single mechanical failure can cascade into a mission-threatening emergency. And that trip, compared to a Mars transit or an interstellar journey, lasted only days and stayed relatively close to Earth the entire time. On a mission to Mars, or especially a multi-year journey toward another star system, an equivalent failure would unfold without any of that real-time support. The communication delay alone would prevent the same kind of rapid back-and-forth problem-solving that mission control on Earth was able to provide during that crisis. Every system has to function, essentially perfectly, for years, decades, or centuries, using only materials and spare components carried from the very beginning. Radiation degrades electronics over time, gradually corrupting memory storage and weakening the semiconductor materials that modern computing depends on. Beyond this slow, cumulative degradation, there's a more sudden version of the same problem. Engineers call it a single event, upset, where one high-energy particle strikes a microchip and flips a single bit of data, turning a 0 into a 1, or a 1 into a 0, potentially without any obvious external sign that anything happened at all. On Earth, thick atmosphere and the planet's magnetic field make this an extremely rare occurrence for ordinary electronics. In deep space, with none of that protection, it becomes a routine, expected event. Spacecraft computers have to be specifically designed to detect and correct for it, often by running critical calculations multiple times in parallel on separate, physically isolated processors and comparing the results. That way, a single corrupted answer can be caught and overridden before it causes real harm. Even with that redundancy built in, the underlying reality remains. Every additional day spent deeper in space is another day of routine. Invisible bit-level errors that engineers have to assume are actively occurring inside every electronic system on board. All the time. Mechanical parts wear down. Seals lose their elasticity in extreme cold. Lubricants can freeze or break down chemically over long enough timescales. And metal fatigue accumulates with every thermal expansion and contraction cycle the spacecraft experiences as it moves in and out of sunlight or through regions of differing temperature. Software encounters edge cases no one anticipated. Situations the original engineers, working decades earlier, simply never modeled or tested for. Engineers who design spacecraft for such journeys have to grapple with a problem that doesn't really exist in ordinary engineering. Building something that must continue working without maintenance from outside for a length of time longer than most human-made structures have ever lasted. There's a related, more personal version of this same problem, the spacesuit itself. A spacesuit is, in effect, a tiny, wearable spacecraft. It maintains pressure, oxygen, temperature control, and protection from radiation and micrometeoroids in a garment a person can move around in. Every layer of that suit is a potential point of failure. Seals around joints, the visor, the connections between the suit and its life support backpack. All of it has to function perfectly during every single spacewalk. Near Earth, if a suit malfunctions, an astronaut can typically get back inside a spacecraft or station within minutes. There have already been close calls, even at this short distance, including an incident where water began pooling inside an astronaut's helmet during a spacewalk, threatening to obstruct his vision and even his ability to breathe. He was only saved because the crew was able to get him back inside quickly. On a mission far from Earth, with no quick path back to a fully equipped medical bay and no possibility of an emergency resupply of replacement parts, a similar malfunction carries dramatically higher stakes. There is no version of that emergency that resolves itself in minutes if the nearest full repair capability is millions of miles and many months away. The farther the destination, the longer that unbroken chain of perfect function has to hold. And the more ways there are for something, somewhere, eventually to fail. So, here's the question. If space becomes more dangerous, the farther you travel, why explore it at all? The answer isn't that the danger is exaggerated, because it isn't. Every hazard described here is grounded in measured physics, from the trapped radiation of the Van Allen belts to the communication delays dictated by the fixed speed of light. The answer is that exploration has never been about eliminating danger. It's been about understanding it well enough to manage it, layer by layer, one engineering solution at a time. Spacecraft shielding has improved dramatically since the earliest missions. Modern designs incorporate materials specifically chosen because they're effective at slowing high-energy particles without generating excessive secondary radiation. Materials like polyethylene, which contains a high concentration of hydrogen atoms that happen to be particularly good at absorbing certain kinds of cosmic radiation. Some mission designs go further, proposing dedicated storm shelters within a spacecraft. Small, heavily shielded compartments, sometimes using stored water or food supplies themselves as part of the shielding mass. A place where a crew could retreat during a solar particle event and wait out the worst of the radiation until it passed. Researchers have also studied more exotic approaches, including active shielding concepts that would generate an artificial magnetic field around a spacecraft, mimicking, on a small scale, what Earth's own magnetic field does for the entire planet, deflecting charged particles before they ever reach the hull at all. So far, no design has proven light enough or power efficient enough to be practical for an actual mission. But the research continues. Passive shielding alone, simply adding more mass, has real limits, both in terms of how much a rocket can actually launch and, as already discussed, in terms of the secondary radiation thick shielding can sometimes create. Radiation forecasting now allows mission planners to time departures and activities around solar activity with far greater precision than was possible during the Apollo era. Continuous monitoring of the Sun's surface can anticipate flares and coronal mass ejections hours or sometimes days before they would otherwise arrive unannounced. Closed-loop life support systems recycle air and water with increasing efficiency, extending how long a crew can survive without resupply. Current systems on the space station recover well over 90% of water from sources that would otherwise be lost, including moisture from the air, and, after extensive purification, even water reclaimed from urine. Oxygen aboard the station is generated primarily by splitting water molecules apart using electricity, a process called electrolysis. That produces breathable oxygen along with hydrogen that's either vented or, in some configurations, combined with carbon dioxide scrubbed from the cabin air to produce more water and close the loop even further. Carbon dioxide itself has to be actively removed from the air, continuously. A closed cabin, with people breathing inside it, would otherwise build up dangerous concentrations within hours. Any failure or clog in the scrubbing system, even a temporary one, can cause carbon dioxide levels to rise quickly. Enough to cause headaches, impaired judgment, and in severe cases, loss of consciousness among the crew. None of this eliminates the fundamental hostility of deep space. But it manages it, piece by piece, mission by mission. The same way earlier generations learned to manage the hostility of oceans, of high altitude, of environments that once seemed entirely beyond human reach. The difference with space is one of scale. The ocean's dangers, however severe, occur within a planet that is otherwise built to support human life. Breathable air, just above the surface. Rescue vessels that can reach a stranded sailor within hours or days. And a temperature range that, while sometimes fatal, rarely approaches the extremes found just a few hundred miles straight up. Space offers no such foundation anywhere beyond Earth's thin, protective shell. Every mission outward has to bring that foundation along artificially, in the form of a spacecraft, a suit, a habitat. And every mile of additional distance adds new dangers that foundation has to withstand. So, what does the honest picture look like once you put every layer together? Near Earth, in low orbit, danger comes primarily from debris and the ever-present need for precise tracking and maneuvering, along with the relentless thermal cycling of swinging between sunlight and shadow every 90 minutes. A little farther, and you cross bands of trapped radiation intense enough to require careful timing just to pass through safely. At the distance of the Moon, you're exposed to the sun's full fury, its wind and its flares and its occasional violent eruptions, with almost nothing standing between you and them. On top of a surface environment that swings between scorching heat and bitter cold across every single lunar day and night. Traveling toward Mars, that exposure stretches across many months, compounded by galactic cosmic rays that are nearly impossible to fully shield against, and by bone and muscle loss that accumulates the entire time, on top of a communication delay that removes any hope of quick guidance from home. Near the outer planets, radiation from the planets themselves can exceed even what the Sun produces. That turns moons like Europa into environments that are scientifically fascinating, and, for an unprotected human, almost immediately lethal. At the edge of the solar system, cold and darkness dominate, and the Sun's protective bubble thins to almost nothing. And beyond that, in true interstellar space, every protection disappears at once. No planetary shield, no strong solar shield, no quick path home, no real-time contact with anyone. Radiation and cold that are, for all practical purposes, permanent and unrelenting. Each step outward doesn't just add distance. It strips away another layer of the protection Earth gives you for free, and adds another hazard in its place. That's the real reason space gets more terrifying the farther you go. It's not that the universe is actively targeting anyone. It's indifferent. And indifference at that scale is its own kind of danger. Nothing out there is going to adjust itself to keep you safe. You either bring the safety with you, engineered, tested, redundant, and reliable for as long as the mission requires, or the environment will eventually find the one thing you didn't shield against. There's a question that scientists have wrestled with for decades that connects directly to everything just described, sometimes called the Fermi paradox, named after physicist Enrico Fermi. Given the sheer number of stars in the galaxy, many of them older than our own sun, why haven't we detected any clear evidence of another advanced civilization out there? Among the many proposed explanations, one stands out as directly relevant to tonight's subject. An idea sometimes called the Great Filter. The possibility that there's some extremely difficult barrier standing between simple life and a civilization capable of spreading permanently beyond its home planet. A barrier so difficult that almost nothing that reaches early stages of development actually makes it all the way through. Everything described tonight offers one plausible piece of that explanation. The radiation, the isolation, the impossibility of quick rescue, the sheer engineering demands of keeping a closed system alive for years or generations. Perhaps interstellar travel isn't simply difficult. Perhaps it's difficult in a way that filters out almost everything that attempts it. A barrier built directly into the physics of distance, radiation, and time, rather than into any failure of ambition or intelligence. This remains speculation, not established fact. And there are many other proposed explanations for the same puzzle. The hostility of deep space explored throughout tonight's journey may not just be an inconvenience for our own species to engineer around. It may be one of the more fundamental reasons the universe, despite its enormous size, still appears so quiet. There's a broader point buried in all of this, one that goes beyond radiation counts and shielding requirements. Earth's safety was never guaranteed to feel special, because it's the only environment most of us will ever know firsthand. But measure it against everything just described. Low radiation, breathable air, moderate temperatures, a strong magnetic field, liquid water on the surface. It becomes clear how unusual this specific combination actually is. Every other environment explored so far in this solar system fails to provide at least one of these conditions. And most fail to provide almost all of them. Mars lost its global magnetic field billions of years ago and lost most of its atmosphere along with it. A slow bleeding away of protection as the solar wind gradually stripped lighter atmospheric particles into space once the planet's magnetic shielding weakened. Venus has a thick atmosphere, but surface temperatures hot enough to melt lead, and pressure 90 times that of Earth's. Conditions so extreme that every lander sent to its surface has stopped functioning within a few hours. Cooked and crushed by an atmosphere dominated by carbon dioxide and thick clouds of sulfuric acid. The moons of the outer planets often have water, sometimes in enormous quantities beneath icy crusts. More liquid water, in some cases, than exists across all of Earth's oceans combined. But they're bathed in radiation from their host planets that would make surface habitation deadly within hours. Interstellar space offers essentially nothing at all. No warmth, no shielding, no material resources within easy reach. Earth, by comparison, is not just habitable. It is layered with overlapping, mutually reinforcing systems of protection that took billions of years to develop and stabilize. A planetary magnetic field generated by a still active molten core, an atmosphere thick enough to burn up incoming debris and block most harmful radiation. A distance from the sun that keeps water liquid across most of the surface. And a moon whose gravitational influence helps stabilize the tilt of the planet's axis, keeping the climate relatively steady over long timescales. There's one more layer: plate tectonics. The slow, continuous movement of Earth's crust that most people never think about at all. It plays a quiet role in regulating the planet's long-term climate, cycling carbon between the atmosphere, the oceans, and rock over immense stretches of time, helping to prevent the kind of runaway greenhouse effect that turned Venus into the crushing, superheated world it is today. As telescopes have grown more powerful, astronomers have identified thousands of planets orbiting other stars. A meaningful number of them sit within what's called the habitable zone, the range of distance from a star where temperatures would theoretically allow liquid water to exist on a rocky surface. But distance from a star turns out to be only one factor among many. None of the exoplanets discovered so far have been confirmed to have anything resembling Earth's full combination of protections. An active magnetic field, a stable, oxygen-rich atmosphere of the right thickness, plate tectonics, a large stabilizing moon, all working together at once. Many candidate planets orbit smaller, dimmer red dwarf stars, which are far more prone to violent flares than our own sun. Flares intense enough that they could strip away a nearby planet's atmosphere entirely over time, leaving even a planet at the right distance with none of the protective layering that makes a world genuinely survivable. Remove any one of these layers, and the others would struggle to compensate. Every layer depends on the others. It's an extraordinarily specific, extraordinarily fortunate configuration. And understanding just how hostile the alternative is, region by region, distance by distance, is what makes that configuration so remarkable. This is also precisely why the search for life beyond Earth has increasingly focused not just on finding a planet at the right distance from its star, but on finding a world that might have managed to build up some of these same layers of protection independently. A planet without a magnetic field, even one sitting at a comfortable distance from its star, could have its atmosphere gradually stripped away by stellar wind over billions of years. The same slow process believed to have happened to Mars. It would leave a world that might once have been promising reduced to a thin, cold shell, offering no meaningful shelter at all. Every layer described tonight that protects Earth is also, in effect, a checklist scientists now use when evaluating whether a distant world might be capable of supporting anything resembling complex life at all. So far, across every planet and moon examined in detail, nothing found has matched Earth's particular combination completely. There's one more scale to this. Beyond the nearest handful of stars, out toward the denser regions of the galaxy, new hazards appear. Hazards that don't exist anywhere near our own solar system at all. Closer to the crowded center of the galaxy, stars are packed together far more tightly than they are out in our own quiet neighborhood. Our own neighborhood sits in a relatively sparse spiral arm. That crowding means a higher chance of encountering the aftermath of violent stellar events. Supernovae, the explosive deaths of massive stars, release a burst of radiation so intense that any planet within a certain distance could have its atmosphere seriously affected. Generally estimated at around 25 to 30 light-years for the most damaging effects. High-energy radiation capable of depleting a significant portion of a planet's protective ozone layer within months, exposing the surface below to dramatically increased ultraviolet radiation from its own star for years afterward. Fortunately, no star anywhere near that distance from our own Sun is currently expected to go supernova anytime soon. But the fact remains that in denser regions of the galaxy, the background rate of these events climbs substantially higher. And so does the associated radiation risk, compared to what we experience in our own relatively isolated corner of the Milky Way. Near the very center of the galaxy sits Sagittarius A, a supermassive black hole with a mass millions of times that of our own Sun. The region surrounding it is a genuinely violent place, filled with intense radiation, densely packed stars whose gravity interacts in complicated and sometimes destructive ways, and energetic events driven by material spiraling into the black hole itself. Astronomers have tracked individual stars orbiting extremely close to this black hole. They move at speeds reaching a significant fraction of the speed of light during the closest points of their orbits, whipped around by gravity far more intense than anything found anywhere near our own Sun. In 2022, astronomers released the first direct image of the region immediately surrounding Sagittarius A. They captured it by linking radio telescopes across the entire planet into a single planet-sized virtual instrument. It revealed a glowing ring of superheated material swirling around the black hole's shadow. The closest humanity has ever come to actually seeing this violent environment directly, rather than inferring its properties indirectly. A hypothetical planet orbiting a star anywhere near the galactic center would face a night sky utterly unlike our own, crowded with far more visible stars than Earth's sky shows, but also bathed in significantly higher background radiation from the dense stellar activity and the energetic environment surrounding the black hole at the center of it all. It's a fascinating region to study from a safe distance, but it's about as far from hospitable as any environment in the galaxy could be. And beyond even the galaxy itself, between one galaxy and the next, lies a scale of emptiness that makes interstellar space look crowded by comparison. The distance between the Milky Way and its nearest large neighbor, the Andromeda Galaxy, is about 2.5 million light-years. A distance so large that light itself, the fastest thing in the universe, takes 2.5 million years just to cross it. The regions of space between galaxies are called intergalactic space. They're emptier still than the space between stars within a single galaxy, containing on average just a single atom or so per several cubic yards. A vacuum so profound it's difficult to recreate even in the most advanced laboratories on Earth. Nobody is proposing crewed missions to intergalactic space. Not now. Not in any near-term plan. The distances involved make even the journey to the nearest star look almost trivial by comparison. But the pattern holds even at this unimaginable scale. The farther out you go, the less there is. And the less there is, the more indifferent and merciless the environment becomes to anything trying to survive within it. Zoom out even further, past individual galaxies entirely, and the universe reveals a structure on the largest scales that makes even intergalactic space look almost crowded. Galaxies are not scattered randomly through the universe. They gather into clusters. Clusters gather into larger superclusters, arranged along vast filaments, threads of galaxies, stretching across hundreds of millions of light-years, separated by enormous regions containing almost nothing at all, called cosmic voids. Some of these voids span hundreds of millions of light-years across, containing only a scattering of isolated galaxies, where a densely populated region would normally hold thousands. A hypothetical observer, situated deep inside one of these voids, would look out at a night sky containing almost no visible galaxies at all in any direction. A darkness even more profound and complete than anything experienced within a galaxy like our own. Astronomers mapping the large-scale structure of the universe have found that our own galaxy sits near the edge of one such supercluster. A vast, loosely bound region containing tens of thousands of galaxies spread across hundreds of millions of light-years, itself bordered by emptier regions on multiple sides. A reminder that even galaxies, as enormous as they are themselves just another layer in a structure that repeats the same basic pattern at every scale examined so far. Clusters of activity and warmth, separated by increasingly vast stretches of cold, dark, nothing. There's a further, quieter danger built into the very structure of the universe itself, one that has nothing to do with radiation or temperature at all. The universe is expanding, and that expansion is accelerating. It's driven by something scientists call dark energy, a phenomenon whose underlying cause is still not fully understood. Because of this accelerating expansion, most of the galaxies currently visible in our sky are over sufficiently long timescales, moving away from us at ever-increasing speeds. Many of them are already moving away fast enough. That light, leaving them today, will never actually reach us, receding beyond what's called the cosmic horizon. Billions of years from now, an observer in our galaxy would look out and see far fewer galaxies than we do today. Not because those galaxies stopped existing, but because the space between us and them will have stretched so much that their light simply can't outrun the expansion to ever arrive. It's a strange, almost unsettling kind of distance, one that doesn't require traveling anywhere at all to experience. Distance that increases on its own, permanently, removing entire galaxies from the reach of any future traveler, regardless of how advanced their technology eventually becomes. There's a final layer of uncertainty here, and it applies to almost everything described tonight. The vast majority of the universe's total mass and energy is not made of the ordinary matter that stars, planets, and people are built from at all. Current measurements suggest that ordinary matter accounts for only around 5% of the universe's total content. Roughly 27% is something scientists call dark matter, detected only through its gravitational influence on galaxies and never directly observed. And the remaining majority, well over half, is the dark energy already mentioned, responsible for the accelerating expansion of the universe itself. In other words, the overwhelming majority of everything that exists remains, in a very real sense, not understood at all. Not even in terms of what it fundamentally is. Every hazard catalogued in this journey, from orbital debris to galactic cosmic radiation, comes from the small 5% of the universe that scientists can actually study directly. What role, if any, the remaining 95% might play in the risks facing any future long-duration journey through deep space is a question nobody can currently answer, simply because so much of it remains, by definition, outside the reach of direct observation and measurement. That's not meant to be an alarming thought, only an honest one. The universe explored throughout tonight's journey, hostile as it already is only the small, visible portion of a far larger and still largely mysterious whole. None of this means humanity should stop looking outward. If anything, understanding exactly how the danger escalates is what allows real progress to happen at all. A threat that is measured, mapped, and understood is a threat that can eventually be engineered around. A threat left vague and unexamined is one no amount of courage alone can properly prepare for. Engineers can't design shielding against a threat they haven't measured. Mission planners can't build in appropriate safety margins without knowing precisely how communication delays, radiation exposure, and equipment reliability change with distance. Every crewed mission that has ever succeeded, from the earliest orbital flights to the missions currently being planned for Mars, has succeeded for one reason. The people involved took the hostility of space seriously, rather than downplaying it. They built systems specifically to counter it, layer by layer, exactly matching the layers the environment itself presents. That approach, taking the danger seriously rather than minimizing it, is really the only approach that has ever worked. In every environment humans have ever pushed into, on Earth or beyond it. The picture that emerges isn't one of despair, it's one of scale. Space doesn't get more dangerous because something out there wants to cause harm. It gets more dangerous because every mile of distance removes one more piece of the protection a single rare planet happens to provide for free, and replaces it with nothing unless something is deliberately built to replace it. That's the pattern, from low orbit all the way out to the space between the stars, and even beyond that to the space between entire galaxies. Not a sudden wall of danger, but a gradual, compounding accumulation. Hazard added onto hazard, the farther out you travel. And it's precisely because this pattern is understood, mapped, and measured that missions can still be planned responsibly, choosing where the risk is acceptable and where it currently is not, and pushing that boundary outward only as fast as the engineering can reliably support it. So the next time you look up and see a clear night sky scattered with stars, remember what separates you from that view being lethal rather than beautiful. A magnetic field you cannot see. An atmosphere you rarely think about. A precise, stable distance from a star that could just as easily have placed this planet somewhere far less forgiving. Every mile beyond that thin shell of protection adds a new way for the universe to become dangerous. Radiation belts, solar storms, planetary magnetospheres more intense than our own, the long, silent cold of the outer solar system. And finally, past the edge of the sun's influence, an unfiltered exposure to the galaxy itself, with communication delays measured in years and rescue not measured at all, because it simply isn't possible. Every one of the hazards described tonight was once completely unknown, discovered only because someone, at some point, built an instrument sensitive enough to measure it, or flew a mission brave enough to encounter it directly. The Van Allen belts were a surprise in 1958. The full severity of galactic cosmic radiation only became clear through decades of accumulated spacecraft data. The boundary of the heliosphere was only actually crossed and confirmed within the last decade and a half. Each discovery added another layer to the honest picture of just how hostile this journey outward really is. And there is little reason to think the layers already mapped represent the complete list. Every new mission that travels a little farther than the last tends to find something the previous generation of scientists hadn't anticipated at all. Space doesn't become terrifying all at once. It becomes terrifying, gradually, one boundary crossed after another, each one quietly removing something you never noticed was protecting you, until it was gone. That's the real answer to why space gets more terrifying the farther you go. It's not a single monster waiting out there. It's an accumulation, patient and indifferent, of everything Earth normally keeps away from you, revealing itself one layer at a time to anyone willing to keep traveling outward. And perhaps that's the most useful way to hold on to everything covered tonight. Not as a list of reasons to fear the sky, but as a map of exactly what stands between comfort and catastrophe at every distance from home. A map that grows more detailed every time a new mission pushes a little farther than the one before it. And a map that, piece by piece, is what actually makes venturing outward survivable at all. Thank you for joining me on this journey through the widening dangers of deep space. If you found this exploration valuable, a like or subscribe helps us continue making these deep examinations of the cosmos. And remember, every mile you are from this planet is a mile further from the protection that makes your existence possible without even trying. Earth gives that protection away for free, silently, constantly, in layers so complete that most people never even notice they exist. Out there, nothing is free. Everything has to be built, carried, and maintained, or the universe will eventually show you exactly how unforgiving distance can be. Good night.